So you probably already have a sense for what kind of bond something's going to do, because you can say, oh, well, for the NaCl, that's ionic. And, that's the left side of the chart, the right side of the chart. You got your stair step right there, and they're on opposite sides of the stair step, and that completely works, and that's really good. So what Pauling did is he said, okay, let's actually look and see if there's a numerical way to quantify and say who's more ionic and who's less ionic. And this helps us when we're figuring out reactions and what reactions will do, and maybe how polar something is. So we're going to zoom in right over here. So that NaCl I just circled, if you look at where its value is on the chart, over here, 0.9, and over here, we've got chlorine is 3. So we just go ahead and we say 9 minus 3. It's just absolute value. That difference is 2.1. So he said, okay, here's our scale. If we're ionic, you're going to be greater than 1.8. And so this is kind of like a numerical way to quantify it. And as you get closer and closer into 1.8, you are going to be less and less ionic and have less ionic character. And when you are ionic, remember you have completely different properties than when you're covalent. And if you're covalent and you have this polarity magnet thing going on, well, then it's even, you have different properties than something that's purely covalent. So sometimes I think of the polar covalent as like kind of an in-between extremes of ionic and pure covalence. Now we're going to look at another one. Here's hydrogen. Now over here on our chart, hydrogen has kind of a funny placement. Remember, sometimes helium could be here, sometimes hydrogen could be here. Those top two elements can be funny. So he falls right there actually. And remember, hydrogen's a non-metal. It's the only non-metal that's not on the right-hand side. Again, it's funny. And when we put it with, over here, we were putting it with that chlorine. Right here, we already have chlorine's value. So you can see how if it were placed over here, and it's not that far from the chlorine, they both are on the non-metal side. So you probably would say, oh yeah, that is covalent. And then the question becomes, how covalent is it? So we look over here and we can say, okay, so here's our difference, 2.1 and 3.0. That difference is 0.7. So what Pauly has figured out is he said, if something has between 0.4 and 1.8, then it is polar covalent. It will have polar covalent properties. And then we're going to go on, CCl. There's our carbon. And our chlorine, I've circled him so much you can't see his value over there, but he's 3.0. And when you look at that difference, that gives us a value of 0.5. And so again, that falls between, and so those are both going to be polar covalent. Lastly, I need to make an addition here. If your chart doesn't have it, it should. That's actually supposed to be including 0.4 and less. And on this chart, we have H. And then if you look at C is 2.5, that difference is 0.4. This is really important, and you're going to find out more about this in organic chemistry, and actually also when we're looking at ionic molecules. I'm sorry, at other covalent molecules. But the reason this is a big significant thing is because your body is made mostly of carbon, hydrogen, backbones here. And so it's really important to look at that and be able to understand that that is a non-polar background. You might see, oh, well, this looks like such a tiny difference. Why are you guys even paying attention to this? Well, it's more that the molecules care, not us. I mean, obviously we care, but I'm just saying it's the molecules that are doing this. We aren't saying, oh, this is the rule, and the molecules are following our rule, right? We are observing the molecule, and then this is our explanation for what it does. And then lastly, when you have the last two things, right, there's no difference because they can pull equally. Now, I want to give a little note of caution here on this 2.1 and these numbers. If you Google this, you will find other values for electronegativity. You might find 4.01. You might find this one to be like 3.1. The whole point is that the trend is the same and that this isn't going to mess up our decisions about whether or not something is covalent or not covalent. It just has to do with our instrumentation gets better and better. And what you'll find on the internet often is the very most updated form of information. Lastly, this word bond dipole, I just wanted to comment, when something has this polarity to it up here that we've talked about, or it falls in that category over here, so polar things, when we're looking at the bond, we'll say the bond has a dipole. Remember, I already showed about this. And I already showed that you can represent it in two different ways. Dipole magnets have two poles, 1, 2. dipole. It just means the bond has two poles. So it's not new information. It's just saying whenever a bond has polarity, it's called having a bond dipole.